Welcome back to part 2 of lecture 7. This lesson is concerned with the factors that affect the pumping performance of the heart. And the factors are preload, afterload, and contractility. In fact, almost any question, quiz, final, step 1, that pertains to stroke volume or ejection fraction or cardiac output, the answer will almost certainly take into account preload, afterload, and or contractility. In part 1 of this lesson, we covered preload and its effects on pumping performance, as explained by the Frank-Starling length-tension relationship. Now in part 2, we'll finish up by considering afterload and contractility. Recall that afterload is defined as the pressure that the ventricle must work against to eject blood. In other words, it's the pressure that the ventricle must overcome in order to push the blood into the arterial tree. And normally we can assume that afterload is aortic diastolic pressure, unless of course aortic stenosis adds an additional resistance to ejection. So left ventricular afterload, like arterial pressure, is normally a function of systemic vascular resistance. Think about 3 situations in which left ventricular afterload is increased: hypertension, of course, aortic stenosis, and vasoconstriction. We'll talk about each one of these. In the laboratory, we can model afterload stresses by asking an isolated muscle, like a papillary muscle, to lift weights of increasing mass. So here's our rack in which we can adjust the degree of stretch that we apply on the papillary muscle. And in this apparatus, we can add a weight that the muscle must lift in order to shorten. In other words, an afterload. So let's perform a little experiment. Here we graph the muscle's length. So in this direction, the muscle will be shortening as a function of time. So in this experiment, we call upon the muscle to shorten while not burdened by any afterload. And notice when we stimulate, the muscle contracts rapidly and shortens to a great extent. If we burden the muscle with greater and greater loads, it will shorten slower, it won't contract as much, and the twitch will be briefer. In addition, as we burden the muscle, the onset of contraction will be delayed. So we can conclude, when subjected to a greater afterload, the muscle will shorten slower, the muscle will shorten less, and the shortening will begin later and end sooner. So how does this effect manifest itself in the heart? When the ventricle must pump against a greater arterial pressure, a greater afterload, the ejection will be slower, lower in volume, and briefer. All of these effects will reduce the pumping performance of the heart. So in patients with a failing heart, one of the first things we want to do is to lower the arterial blood pressure. Why? By reducing afterload, we improve the stroke volume and we lessen the workload on the heart. We'll learn that pressure work by the heart is energetically expensive. We want to convert pressure work into volume work by reducing the afterload. So let's prove this to ourselves with a ventricular function plot. The red curve shows the Frank-Starling length-tension relationship, which indicates that as the heart fills with greater volumes of blood in diastole, the ventricular myocytes will stretch to a greater degree, and as a consequence, they will be able to generate more force, more pressure. Recall that we can model a single cardiac cycle by superimposing a PV loop on the ventricular function curve. We start here in diastole with a residual volume, an end systolic volume of about 50 mils. The heart fills, and when the heart contracts, we first have isovolumetric contraction. The ventricle is actually capable of developing a much higher pressure, but as soon as the ventricular pressure exceeds the aortic diastolic pressure, we get ejection, and we return to another cardiac cycle. Suppose, however, if we suddenly increase the aortic pressure from 90 to 130 millimeters mercury. Now the ventricle must develop more pressure in order to eject, and now we get ejection until it intersects the ventricular function curve here. As a result, the stroke volume is reduced from 65 mils to about 40 mils. So what happened? When the heart is made to pump against a greater afterload, the ejection fraction decreases. More blood remains in the heart at the end of systole. Now consider what will happen on the very next beat. Assuming that the rate of venous return is unchanged, Another 65 mils of blood will enter the ventricle. And since the ventricle could not eject all of the blood on its previous cycle, this blood will add to the next end diastolic volume. And as the Frank-Starling law tells us, the dilated ventricle will pump harder to eject the blood on the very next systole. So the Frank-Starling effect has compensated on the next cardiac cycle. In other words, it has restored a stroke volume, and the ventricle will continue to eject what is presented to it even at the higher afterload. Recall that the Frank-Starling effect is responsible for matching cardiac output to venous return. And now we return to this very important point. The force at which the heart contracts can be changed in only two ways. We can change the initial fiber length, we can stretch the fiber, and when stretched, the fiber will develop a greater force of contraction. The only other way to increase the force of contraction is through a change in contractility. And this is seen at the same initial fiber length. So this has nothing to do with the Frank-Starling mechanism. Another word for contractility is positive inotropy. So what is contractility? Let's explore that further. Contractility, or inotropy, is a term that describes at a constant initial fiber length the vigor of contraction, which is reflected in the rate of change of pressure as a function of time during systole, or the ability to develop pressure, or the slope of the ventricular function curve. And this pumping performance is reflected in ejection fraction. The contractile state of the myocardium is improved by circulating hormones, especially norepinephrine and epinephrine, and likewise the catecholamine neurotransmitters at the sympathetic nerve terminals. And various drugs can improve the contractility of the myocardium. The contractile state of the myocardium is also impaired in disease, ischemic heart disease, where the muscle fibers are not receiving enough nutritive blood flow to support their basic metabolism. So they begin to fail and they lose the ability to develop force when excited. In acidemia, local extracellular acidemia is a major negative inotrope in the heart. Conduction defects. The heart may be receiving enough blood and contracting, but a conduction defect may cause the heart to contract in an inappropriate, uncoordinated way. And one final example is loss of myocardium, where you have a zone of the myocardium that has been deprived of adequate blood flow and it has become permanently injured or dead. So let's go back to our ventricular function curve and model an increase in contractility and look at its effect on stroke volume. Here we have the ventricular function curve. We've superimposed a normal PV loop, one cardiac cycle. A shift in contractility is manifest as a shift in the ventricular function curve. Suppose we stimulate the sympathetic nerves that innervate the heart, or we expose them directly to the neurotransmitter norepinephrine. That will stimulate the working myocardial cells and cause them to develop more force at every given volume. And now when the ventricle contracts under the influence of norepinephrine, it will intersect the new ventricular function curve way back here. And now we'll see an increase in stroke volume due to a decrease in the end systolic volume. In other words, the ventricle will contract with greater force and vigor, and less blood will be left in the ventricle at the end of systole. How can we model a decrease in contractility? Decreased contractility or negative inotropy can be caused by hypoxia or acidosis or myocardial ischemia, inadequate blood flow. And all of these factors can contribute to the loss of contractility that is commonly seen in heart failure. At any given preload, the failing heart will be capable of developing less pressure and therefore will eject less blood. Let's look at this in the PV loop, shown here in blue. Now when the failing heart ejects, it will intersect a ventricular function curve, which is lower and shifted to the right, and this will produce a lower stroke volume. So this will leave a larger volume of residual blood in the ventricle at the end of systole, and the ejection fraction will be decreased. But on the next beat, the venous return will add to the higher residual volume left in the ventricle from the previous ejection. So now stroke volume will be restored by the heart operating at a higher filling volume, taking advantage of the Frank-Starling length tension effect. And this is what happens in a failing heart. Here is a normal heart, and here is a heart in early failure. Notice that the heart is dilated. This is in part due to the heart's requirement to operate at higher filling volumes. And by doing so, it takes advantage of the Frank-Starling length-tension relationship. The operation of the ventricle at high filling volumes is an initial beneficial adaptive response that helps restore stroke volume in a failing heart. However, continued operation of the failing heart at high volumes, high distension, high EDVs, has many long-term detrimental effects. So don't worry if this is all a bit confusing to you right now. We're going to cover congestive heart failure in much greater detail in a later lecture. Remember that sympathetic nerve fibers project to all parts of the heart: the SA node, the AV node, the conduction system, and nearly all of the contractile cells of the myocardium. And these nerve terminals release norepinephrine, which binds to and activates adrenoreceptors. The most important adrenoreceptor in the heart is the beta-1 subtype. Activation of this receptor, which is coupled to adenylate cyclase through the GS protein, has three effects. First, acting at the SA node, the beta-1 receptor increases heart rate. Remember, this is called positive chronotropy. And acting in all of the contractile cells, the working myocardium, this receptor increases contractility. This is called positive inotropy. And in the conduction system, activation of the beta-1 receptor by norepinephrine increases conduction velocity, and that is called positive dromotropy. But we will learn that the persistent activation of the beta-1 receptor over the course of weeks and months in heart failure promotes hypertrophy of the muscle cells. And this form of hypertrophy is a destructive remodeling of the myocardium, and it is in part driven by the beta-1 adrenergic receptor. So you will be prescribing fairly soon beta-1 blocking drugs like atenolol or metoprolol. Beta blockers all end in laughing out loud, LOL, atenolol, metoprolol, and you will be prescribing these drugs, these beta blockers, to your patients with ischemic heart disease and congestive heart failure. And this is done to decrease the workload of the failing heart and also to prevent that detrimental remodeling of the myocardium that occurs over the long term in heart failure due to the bombardment of the beta-1 receptor in the heart with persistent sympathetic drive. So let's go back and consider the effect of norepinephrine on the pumping performance of the heart. Recall, here we see the release of calcium inside the myocyte in response to a membrane depolarization and the resulting contraction of the myocyte. So notice that under the influence of norepinephrine, the action potential is shorter, more calcium is released faster, and the calcium is resequestered faster. And as a result, the contraction is stronger and shorter. Think about how this might affect the pumping performance of the ventricle. The stroke volume will be larger. The ejection will be faster, more vigorous, and the ejection fraction will be higher. There will be less blood left in the ventricle after a more vigorous contraction in systole. So how does this occur on a cellular level? Here we have a cardiac myocyte. The beta-1 receptor is coupled to adenylate cyclase, which converts ATP into cyclic AMP. Cyclic AMP then goes on to activate protein kinase A, which goes on to phosphorylate various proteins, including the L-type calcium channel in the plasma membrane. And when phosphorylated, the open probability of the calcium channel is increased, and then for every depolarization of the membrane, the L-type calcium channel admits more activator calcium into the cell. pKa also phosphorylates the calcium-induced calcium release channel on the sarcoplasmic reticulum, and when phosphorylated, this channel allows more calcium to be released from the SR. So, with more activator calcium and more calcium released from the internal stores, there is more calcium to flood the myofilaments and cause contraction. Protein kinase A also phosphorylates a regulatory subunit of the SERCA calcium channel in the SR, and its phosphorylation stimulates the calcium pump. So the calcium is resequestered back into the SR more vigorously, and this has two effects. First of all, it loads the SR with more calcium in between beats, and second, it hastens the removal of calcium from the cytosol back into the SR and therefore speeds up relaxation. So the net effect is more calcium delivered to the myofilaments, resulting in a stronger contraction, and then faster calcium reuptake, which gives a faster relaxation. You may have heard of a drug called digitalis. Digitalis is a steroid-like molecule that is extracted from a flower, the purple foxglove. And it's been used to treat heart failure since the time of William Withering, who wrote about 250 years ago that digitalis has a power over the motion of the heart to a degree yet unobserved in any other medicine. Digitalis is a member of a group of drugs called cardiac glycosides, and these drugs improve cardiac contractility in a very interesting way. Recall that the sodium-potassium ATPase pump operates in virtually all animal cells to trade 3 internal sodiums for 2 external potassiums, and in so doing maintains a steep inward sodium gradient and a steep outward potassium gradient. Now recall that operating alongside the sodium-potassium pump is another exchanger. This one trades 3 external sodiums, internal calcium. So this is a 3-sodium calcium exchanger. And remember that this is the major mechanism for removing the activator calcium that was admitted into the cell by the L-type calcium channel. Digitalis binds to an outwardly facing potassium binding pocket and disables the operation of the pump. So when digitalis is administered to patients at just the right low therapeutic dose, it will partially inhibit the cardiac myocyte sodium-potassium pump, and the sodium inside the cell will increase maybe from 10 to 14 or 15 or 16 millimolar, lessening the inward sodium gradient. Recall that the 3-sodium calcium exchanger operates right on the cusp of thermodynamic equilibrium. In other words, the energy available in the inward chemical gradient of sodium, and in this case it's to the cubed power, is just enough to extrude calcium up a 3 million-fold gradient out of the cell. In the presence of digitalis, the sodium gradient is partially dissipated, and there is no longer as much energy in the inward sodium gradient to drive calcium extrusion. So in the presence of a low therapeutic dose of digitalis, we have a reduced sodium extrusion by the sodium-potassium pump. This leads to a slight increase in intracellular sodium and a reduction in the inward sodium gradient. This reduces the efficiency of calcium extrusion by the sodium-calcium exchanger, and the SR loads with more calcium during each diastole. And with more calcium stored during diastole, more calcium is released during systole, and the resulting contraction will have greater force at any given fiber length. So here's a summary slide which reminds us that a change in preload results in the heart operating at a different position along the Frank-Starling length tension curve. As we increase preload, there is greater diastolic filling, the ventricle stretches, and when the myocytes are stretched, they are able to develop more force. A change in the position of the Frank-Starling curve represents a change in contractility or inotropy. Please do not confuse these two terms. Inotropy is a change in pumping performance at a given fiber length or EDV. And the contractility of a cardiac myocyte can be improved with various hormones or drugs, or it can be impaired in disease. And that concludes Lecture 7. As always, thank you for your attention.